We're into chapter 4. This is the reaction chapter. Here we go. What can I start? I'm going to start with dilution, concentration of ions. Those both go together quite well. Okay. There are three types of molarity problems. One type is the unit conversion. That's if you have one compound of interest and you're going from one unit to another. Okay, and molarity somehow involved. The second type is dilution. We're about to do that. That's where you have one compound of interest, and then the molarity and the volume are changing. Third type is a stoichiometry. That's where you have a reaction. Yeah, more than one compound of interest. This is the only case, stoichiometry. More than one compound of interest. You're doing a stoichiometry calculation, molarity is involved. Yeah, we were going to do concentration of ions. There's a variant of this kind of question. It's a little bit harder. I'll just kind of set it up for us. I don't think I'll solve the whole thing. But I just want to show you how this could kind of work. Let's say we have an MgCl2 aqueous and KCl aqueous. Let's say this was 1 molar. Let's say this is 2 molar. Let's say you have 300 milliliters of this. Let's say you have 100 milliliters of this. And I want to add these together and then find the concentration of only Cl minus at the end. So what's the concentration of Cl minus at the end? Well, some of it's contributed from here, and some of it's contributed from here. So in that case, this is a pretty classic question. You can see this on exam or final. It's a pretty normal style of question. It just is one step more involved than the previous type. What you're going to do is take each part separately, is what I'd recommend. So you're going to go, well, you got 1 molar of that times 300 milliliters. If you want, you can change this to liters. It's not really going to matter in this kind of question, but we'll just do it in case you're going to freak out about it. So, liters. This will end up with what units at the end? Moles. And it looks like we're going to be about 0.3 moles. Okay. Now, that's moles of what? MgCl2 aqueous. Now, if I wanted moles of just Cl2, moles of Cl minus, what would that be? 0.6, how did you get that? Yeah, you got it. There's 2 moles of Cl for every MgCl2, so it's double, because there's 2 Cl's in here. Now you're going to do the same thing. I'll pick a different color here for this one. I'll do it down here. You're going to go 2 molar times 100 milliliters times, convert this to liters. This will also be moles of, now, KCl. And that's going to be 200 over 1,000, 0.2. Is that right? And then if I wanted moles of Cl minus, that would be just 0.2, because there's 1 mole of Cl for every KCl. There's 1 of them in there. So then, I'm merely, to find the final molarity, I'm going to go the total moles of Cl, which would be 0.6 plus 0.2, divided by what number? Yeah, 400 milliliters, or really in liters, it's 0.4 liters. So whatever that number is, looks like it'll be about 2. Will be your final molarity of the combination of those ions. Okay, think about if you have a question on that while I think about what question I'm doing next. Here. Oh, I know what I'll do next. Yes. Okay. And I want to make sure.
I saw this album. Oh my god.
While you're thinking, I'm looking for some additional questions here. See if I have one. Not about what to do. Okay. All right. Questions on this? Way in the back. Has to be super loud. How did I get 0 points for this? It's the sum of the total volume. Change to liters. Because that's where 0.4 is. Okay. Alright. Next. We're going to do, let me mention this, single replacements. Oh, and stoichiometry, I'll do that too. We're flying, we're doing okay for time. I think it was going to go till 9:45. Yeah. First, let me write down a single replacement reaction. I think I have one handy over here somewhere. Let's see if I do. I think I do. Possibly I do. I think this one will work. Oh, no, I don't have one. I think if I have one based on what people are asking. They're a little tough to think of sometimes if you don't have one hand. Let's see if this one will work. Oh, okay, I found one. Yes. Okay, here's a single replacement question. In this, you have a lone metal plus an ionic. So here the manganese is going to be by itself in the end, and then aluminum will go with the sulfate. Aluminum is, when it's in an ionic compound, is +3. What's the charge of aluminum here? 0. Don't say it's +3. It's +3 when it's in an ionic compound. The sulfate, -2. So it's Al2SO4 3. So then I have to balance this. I got to put a 3 there, 3 there, 2 there. I think that'll balance it. All right. You may in another class, not in my class, learn about active metals. So there's like what metals are more reactive than others. This is one thing that some other instructors do now, and I would do in 2C. So, but there's a list of active metals. You either need to, your instructor either needs to give them to you, or unfortunately you need to memorize them. When we get to what's electrochemistry in Chem 2C, there's more information that goes along with these active metals, and that's when I cover it, and then that's kind of covered. But that's to decide if a reaction will happen. There's something I haven't taught yet that I say for electrochemistry to teach that. But you would want to ask, is that list going to be given to me, or do I need to memorize it? And that'll tell you if aluminum will displace manganese or not. If not, it's no reaction. My class, we wouldn't do that. All the reactions are going to go. Yeah. Aluminum or manganese, why does it not have a charge when they're by themselves? Well, first of all, I didn't give it with a charge, so it doesn't have a charge. I had to write a number here. And single replacements work that way. It has to be the lone element with no charge plus this species here, an ionic species. Okay? So then it goes to the lone element with no charge plus the ionic species. So that's a super common mistake, is to put a charge on one of these two. That's not reality. Okay, good. Okay, if you have more questions about the active metals, you can ask me later. Okay, next. Oh, stoichiometry. Let me just do something here. let's say I have 10 grams of this, and I want to know the mass of this. Whenever you're doing a stoichiometry problem, I divide what I call the molar express into 3 steps. Step 1, if you want to do stoichiometry here, would be to say, okay, when I'm starting with 10 grams, I need the molar mass of this, so the periodic table for aluminum, that's 26.98 grams per mole. So first step is to go to moles. So this would be my step 1. Step 2 for me is the molar ratio to get to what I want. There's 1 mole of Al2SO4 3 per every 2 moles of aluminum. So for me that's step 2, that's the molar ratio. Step 3, so this has to be multiplied here, I ran out of space, is to go to the requested unit. So I'd go the molar mass of Al2SO4, I'll let you find that. The molar mass, I put that number in right here, and that will give me the grams of Al2SO4. So one more time, 3 steps that I always use in stoichiometry. Step 1, go to moles from the given unit. Step 2, molar ratio. And then step 3, go to the requested unit. In this case, it was mass of the Al2SO4, which is grams. Okay, so you always see me, if I'm doing this kind of problem, go through those steps. All right, that's stoichiometry. Next thing I want to do, consecutive reactions. This is another one of those, depending on whose class you have, we might approach this slightly differently. So just be forewarned if you're in another class. I don't know how the other instructors approach these kind of problems. You're going to see these kind of problems though. Oh, let's do this one. I showed this one in class, but I never solved it. You're going to see these kind of problems in 2A. You see them with redox. You see them twice in 2B, and then a fourth time in 2C. So I cover them explicitly in 2A for that reason, because you see it 4 times total. Other instructors have you learn it by osmosis, kind of, so you kind of see it here when you do redox, when you add 2 half reactions to get the total. That's called a simultaneous or consecutive reaction. But you see it super explicitly in Chem 2B twice. And then, of course, the 4th time in 2C. So I just decided to go explicitly into A. Other instructors, again, different vibes. So you might be different in different classes. If you want to, if you're in another class, you can zone out for a couple minutes if you didn't learn simultaneous or consecutive reactions. Okay, so how do these work? You have the overall reaction given right here. That's the overall. And these 3 are the simultaneous or consecutive reactions. Those simultaneous need to add up to the overall reaction. So I have a 2-step process in solving this. One is to find any component here that appears only one other time. So what would be a good candidate of these 4? HF appears here and here. That's a good candidate. So I cannot change the overall reaction, but I can manipulate the simultaneous, the 3 down below. So for the first reaction, what will I multiply it by? 2. If I multiply that first reaction by 2, that'll give me 2 times 2, or 4HF in the products. So that's what I want. I want 4HF in the products. So alpha is 2. So the answer is D. But I'll finish the problem in case that wasn't there. But the answer has to be D. Just don't be a goofball. Just like circle it, okay? All right. What's another candidate here? C2H4. I'll do a purple rectangle around it. That works, yeah. So now that's on the wrong side in reaction 2. So, but there's the right number, 1. So I need beta to be -1. That flips the reaction over, which I need to do because C2H4 needs to be in the reactants. D is still looking good. Okay. And then is there any other candidates that kind of work? CF4. I'll put a green triangle around that one. Okay. So I need it on the other side, and I need 2 of them. So I'm going to multiply by. I like it. Thank you, loud voice person. What would happen if this didn't match D here? Yeah, you're wrong, definitely. Okay, so just go back and restart. All right, any questions on this before I go on? All right, next. Limiting reactant problems. And that'll kind of go with percent yield. So let's do a percent yield and limiting reactant problem. That'll finish that chapter of reactions here. Yeah, let's just get rid of all that. Let's see. What was I doing? Oh, I was doing limiting reactant. Let's come up with a reaction. I like that reaction I had earlier, actually. Let me write it down again. I don't know where it went, but it was. And let's balance this again. I forgot what it was. It was 3, 3, and 2. There we go. Okay. Let's say I wanted to know the mass of this. Okay. And let's say I was given 10 grams of this. Is this a limiting reactant problem? Definitely not. It's definitely not. This is what kind of problem? Just pure stoichiometry. Change this to moles, molar ratio, go to the requested unit. This is a limiting reactant problem. It's when you're given information, mass or moles, of 2 or more reactants. 2 is the minimum. When there's, then in mathematically it's what we call overspecified. There's too many numbers and too little variables. So in this case, you have to do 2 stoichiometry problems, 1 going that way and 1 going that way. Okay, so there's 2 stoichiometry problems now. So for example, you'd start with aluminum. You go, okay, I got 10 grams of aluminum. Molar mass, go to moles. So step 1, go to moles, just like I said before, 26.98. Then the molar ratio, 3 moles of manganese for every 2 moles of aluminum. And then the molar mass was 54.94 for manganese, grams per mole. And then you get the grams of manganese. And then you do that all over again with manganese sulfate. Same thing, but you start with its number, 3 grams. First go to moles. I don't have this one memorized. Molar mass of manganese sulfate. Then the mole ratio, 3 moles of manganese for every 3 moles of manganese sulfate. And then the final step is go to the requested unit, mass, and it's 54.94 grams per mole for manganese. This will also give you the grams of manganese. So you're solving in 2 ways. Mathematically, you can't discern between these 2, but chemically, you're going to compare these 2 numbers and pick which number? Whichever one's smaller. You can do this at home with your friends if you want. Okay, I just made it up, so I don't have an answer. All right, you're going to pick the smaller answer. And that'll be your limiting reactant answer. Where it came from, whatever gave you the smaller answer, whichever one of these 2 is the limiting reactant. And then the one that gave you the larger answer is the one in excess. You could be asked to find the mass of the reactant in excess, how much is left over. So in that case, you go from the correct answer back to the one that you were asked about. Okay? All right, that's limiting reactant. That's all I have on that. Any questions? I want to say something about percent yield. Okay, for fun, sometimes this is paired with a percent yield problem because we like to have a lot of fun. So, we would say something like, let's see what color here. For a percent yield, we would say an experimenter in lab actually made 0.01 grams of manganese. What's the percent yield? So then, you have to find the correct limiting reactant answer. And so what you do is find the percent yield. That would be equal to 100% times the actual or the given number in mass. So that's what it says you found in lab, the experimenter found, you found, something like that. Okay, that sort of language. You're going to divide that by the answer from up there. So this is called the theoretical. This is what the person asked about, whoever asked this question. The theoretical answer, or the theoretical yield. So that's the one you calculate. So that, in this case, is your limiting reactant answer. If it was just a pure stoichiometry problem, it'd be your stoichiometric answer. Whatever answer you get for the mass, in this case of manganese, you put in the denominator. You'll get an answer somewhere between 0 and 100. It could include 0 or 100, but it shouldn't be larger than 100 or smaller than 0. Okay. Any questions on limiting reactant? So it's just 2 stoichiometry problems, that's it.